very popular chart I brought here from National Renewable Energy Laboratories in the United States. And we call NREL. And this is very popular chart. And in the horizontal axis, you can see the years started from 1975 till date. And the vertical axis here, we show the solar cell efficiency. And the data here, these are officially tested data, okay? These are not the data only just in some paper. These are the data who have passed through the 3 different testing sites in the world. One is NREL, another is AIST Japan, and the third one is in Germany, okay? So the solar cell, if they pass through this testing site, only their data appear here. And here in this chart, okay, this is very difficult to read, but you see different colors, green colors, you see blue colors, okay? And so the green color here we call thin film technology, solar cell, okay? And within years, their efficiency is increasing. And, okay, but here you see a dotted line. I have drawn a dotted line, the pink dotted line, and this is the thermodynamic limit, which we call Shockley-Quasar limit, and this is 31%, okay? So no matter what, if you just bring a PN junction, okay, in the previous lecture, the professor was talking about the PN junction, and the very similar PN junction for solar cell, photovoltaic cell. So this is the limit, 31% is the theoretical limit. So if you look at the blue dot, these are silicon solar cell on a rooftop, and you see that last around 30 years, this is almost flat. This is silicon solar cell, and this is very flat. There is no improvement. But there are some new technologies, if you look at there, okay, they are breaking this limit, this thermodynamic limit, and they're passing through the limit and going, and okay, the world record, okay, here I'm showing the world record is 46%, and this is big. 46% means out of the 100% efficiency energy coming from the sunlight, we can convert 46%. And very recently, the new world record is 47.1%. And the photosynthesis, in the previous lecture, we have been listening about photosynthesis for our plant. Okay, so the photosynthetic rate, if you consider, it is hardly 1 to 2%. And this rate is, let's say, making our civilization, because whatever the fossil fuels we have out of this photosynthesis. But if you compare to photosynthesis, we already hear 31% limit, and the world record already 47%. So this is great news for our carbon-free technologies. So with this background, okay, let me move fast forward. Okay, so today I'm going to talk about intermediate band solar cell. And in the previous slide, the world record solar cell, we call them multi-junction solar cell. So in our laboratory, we work on multi-junction solar cell, and they require very sophisticated technologies. For example, Professor Tiwari was telling that my expertise is molecular beam epitaxy. These are very sensitive technologies, because we make latest mass technologies and very expensive. So currently, most of the satellite we are for photovoltaic cell, we use our multi-junction solar cells, because they are highly efficient, but they are very expensive. So we only can afford them for let's say satellite, but we want to bring them down to Earth, but they're very expensive. So one way we're doing is today we call concentrated photovoltaics to reduce the cost. Another way we had today's talk, the other way how to beat this cost and the efficiencies is intermediate band solar cell. This is a new concept, and this is pretty new ideas. I'm going to talk about that. And to that new idea, here today, I'm going to quickly talk about 2 different kind of materials. One is 3,5 gallium arsenide based materials, because for the multi-junction solar cell, these 3,5 technologies are the vital technology. Okay, so I'm going to talk about how we can use that 3-5 semiconductor for intermediate band solar cell. And also I'm going to talk about CGS solar cell. Okay, there is another technology we people know in thin film industry, CIGS selenide. But today I'm going to introduce how we can make them usable for the intermediate band solar cell. Okay, and that final part is device design and engineering, how we can make materials to convert to intermediate band solar cells. So so this is a very schematic picture. This is horizontal axis is the wavelength, and the vertical axis is the energy, photon energy coming from our sunlight. And so our sunlight has this kind of distribution. And in a multi-junction solar cell, who has the world record efficiency right now, we split the spectrum into multiple windows, and we allow each window into different semiconductor p-n junction, and we call them multi-junction solar cell. For example, here we have 3 different bandgap solar cells, but in the right side, I show you that in a single semiconductor host, if we somehow allow intermediate band, then we have triple bandgaps: first bandgap, second bandgap, and some third bandgap. So this is very similar to a 3-junction solar cell, but for 3 junctions, multi-junction solar cell, you have to bring 3 different technologies, and you have to overcome different challenges, kind of interface, and tunneling junction. But if you can have a single host semiconductor and bring an intermediate band in between, then effectively this is very similar to 3-junction solar cell. And this is a thermodynamic calculation that if we have somehow, if we can allow an intermediate band, which is IB, between the valence band and conduction band, and if we change the band gap, conduction band and valence band in the horizontal axis, and the vertical axis is the band gap between the conduction band and the valence band, then we have different combination of the band gaps, and the maximum is 63% when your band gap is 1.9 electron volt, and you have intermediate band, down at around 0.7 volt, So if you bring this kind of combination and make your p-n junction, you can make an intermediate band solar cell. So just, so in our group, Professor Okada, he's a pioneer in quantum dot solar cell. He's working with the quantum dot superlattice structure to make intermediate band solar cell. But I'm gonna working not on quantum dot, because quantum dot are require you very sophisticated technologies, strict control of the molecular beam epitaxy and the strain. But these are very cost effective thin film solar cell. I'm going to introduce about that. And we have a review paper. This is pretty much highly cited in this domain, that intermediate band solar cell, the recent progress and future direction. It was published 2015. So some of the ideas we have already published here. So still I'm in the introduction part today, and my time is pushing. Let me, just tell that for the intermediate band solar cell, the very, very important thing we call is two-step photon absorption, If you don't have intermediate band, your infrared light pass through the material. But if you have intermediate band, then the infrared light can be absorbed by the intermediate band, and 2-photon absorption can give you excitation from the valence band to the conduction band. But your Fermi level should be in between, inside the intermediate band. So if you have a very optimized Fermi level in the intermediate band, you see very high absorptions of the electron, and you can see twist of photon absorption. This is just a schematic picture, and in this case we can get high photon current production, due to the current infrared light, due to infrared light. So right here, so one of the world record technologies for the multi-junction solar cell, we use gallium nitride arsenide, for the 4-junction solar cell. But here I show what exactly happened in gallium arsenide if you have a nitrogen doping. For example, here you guys know about gallium arsenide conduction band have this kind of dispersion, and the valence band has heavy hole, light hole, and spin orbit band in the valence band. But if you have a very tiny dilute amount of nitrogen impurity, the impurity state is right here. So here the nitrogen concentration is 0%. This is just a calculation based we call the theoretical calculation. And if you put some amount of nitrogen, then you see the conduction band is split into two bands. One is E plus band, another is E minus band. And this is 1% of nitrogen, okay? And what exactly happened? You see now, if you have three band gaps, the first band gap, second band gap, and the original third band gap, okay, like this. And if you change nitrogen more and more, you see you can play with the band gaps. And the maximum band gaps will show you 63% conversion efficiency. But if you have a single junction solar cell, I already told you the limit is 31%, okay? So making intermediate multiple band gaps give you the opportunity to break the single junction limit. Okay, let me go next. So this is a DFT calculation, density functional theory calculation. If you put little amount of nitrogen in gallium arsenide, then I show you here that we have multiple band gaps, okay? And here I show you that we can play with the absorption coefficient between the triple bands, how you play with the Fermi levels, and I'm not going details, but I want to show you that, play with the Fermi level is the one important technology to improve the two photon absorption. And this is our experiment. These samples we have made by molecular epitaxy, molecular beam epitaxy of dilute nitride, gallium nitride arsenide on gallium arsenide. And these signals from our substrate, gallium arsenide. And these are horizontal axis is the photon energy, and the vertical axis is the photoreflectance signal. Here I want you to show that if you put some amount of nitrogen, this is the reference gallium arsenide signal. If you don't have any nitrogen, you get this kind of band gap. But if you have little bit amount of nitrogen, you increase more and more nitrogen, we have two bands. One band which is lower than the gallium arsenide band gap, another band gap which is higher than the band gap. And with this picture, I draw back again here that with increasing nitrogen concentration, we have extra two band gaps. And by the amount of the nitrogen, we can play with the band gaps, okay? So with that, if we have 1% of nitrogen, in the previous slide, I wanted to show you that by adding 1% of nitrogen, we can reach the theoretical limit of 63%. And here, to demonstrate the two-step photon absorption experiment, we have two light sources in our solar cell, and out of that, we do this kind of experiment to show the two-step photon absorption principle, okay? And we have a paper on this in 2012. And here, using dilute nitride semiconductor material in a solar cell, we have N-type material, we have P-type material. So this is a PN junction, and in between the PN junction, we have intermediate bandgap solar material. And here you see, if we don't have this intermediate bandgap material, you will not see any twist of photon current. This is twist of photon current, okay? It should be straight line, which is this dotted line. But if you have intermediate band solar cell, I show you here that due to that intermediate band state, we have a lot of photon current we can generate. And if you put some amount of antimony in your dilute nitride, because it is well known that if you put nitrogen in gallium arsenide, you have a lot of defects. To avoid that kind of defects or vacancies or antisite, we put some amount of antimony, and we can, I show you that we can improve the materials and we can improve the photocurrent production, but still this is very low, okay? And I'm explaining here how we can explain this kind of photocurrent production using this intermediate band. And next, I show you another material system. This is, so far I'm talking about 3,5 semiconductor compound, but copper, gallium, sulfur. This is a famous 1,3,6 group, but the world record in copper CIGS solar cell use selenide, not sulfur. Okay, because CIGS band gap is 1.1 electron volt, very close to silicon, and that is they have a world record efficiency in thin film solar cell, and the band gap is 1.1. But for intermediate band gap, we need wide bandgap host semiconductor. And if we change selenide to sulfur, we can get the band gap 2.4 electron volt. And here, the first principle calculation, if we have just CGS, okay? So you see a direct band gap here. But if you put some amount of, let's say, transition metal, in this case chromium, now you see you have an extra band between the valence band and conduction band. Now we have extra band due to this impurity. And this is how we can make an impurity band solar material. And then you can make two-step photon absorption. Here you see you have one band gap. Now here you have three band gap at the gamma point. Okay. And this is, okay, I have presented in the photovoltaic conference in the Washington, D.C. 3 years back. And since then, we started a lot of calculations, a lot of materials based on DFT, and we are tuning a different material system. And we are also making, okay, this is calculation that if you have a single band gap, you see single absorption coefficient. But if you have intermediate band gap, in principle, you see you have three band gaps and three different absorption coefficient. This is based on DFT calculation, not experiment, because experiment with this kind of material is very, very challenging. And we started doing the experiment. Okay, this is not through MB, this is using sputtering. Okay, and I here demonstrate that, okay, we can make a good quality copper gallium sulfate thin film. Okay, and we are working hard to make larger grain size and chromium doping. And I show you there that if you optimize the sulfur annealing, we have a very sharp band gap at 2.44 electron volt, because wide band gap is vital for intermediate band solar cell, and we have very good photoluminescence signal out of this thin film. And we are working on this solar cell structure. This is the PN junction. Okay, you have p-type copper gallium sulfur in the bottom side on molybdenum substrate. On top we have zinc oxide and zinc sulfide buffer, zinc oxide, okay, contact. And we are working on this solar cell device right now. Okay, so today I'm going to talk about how we can design, okay, because the existing design rule does not work for intermediate band solar cell. This is a very tricky idea. Okay, now I'm going to talk about that part. So the issue limiting the intermediate band solar cell activity. Okay, so I'm going to talk today about let me, I have set to 20 minutes and it's showing, okay, cancel. I'm sorry, let me allow a little bit, okay. Cancel.
Yeah, you can go ahead, you take your time.
Oh, thank you. So this new concept, this is a new concept I told you, because there is no working solar cell yet, and only few groups are working in this domain. So the main challenge is this intermediate band, how you can, okay, from, you have a valence band down, from the valence band, by the first light you can bring here, but the current can, okay, pass through here. If you have a barrier, the electron can pass. This is a loss mechanism, number 3, which is by tunneling to the contact, and you cannot collect the voltage. For intermediate band gap, it is very, very vital. You get the current, but you should not compromise the voltage. Okay, the voltage, you need a second photon coming from here and excite the electron in number 1 step. This is what we love, but we don't want to see the step 3 or step 2, that this electron go out. You can get current, but you will not get the voltage. So this is the mechanism, okay, that for intermediate band, very two important process, that you have to have a good intermediate band barrier, and you make sure that the electron in your intermediate band should not, okay, escape by the thermal heating or by tunneling. So you should design a good intermediate band barrier. And let's say here, if you're, this is a barrier layer, okay, this is my, let's say, dilute nitride material, okay, here. And this is my contact layer, backside and front side, but this is the barrier. The electron coming here should not pass through here, but I have a very thin barrier here, so my electron will tunnel through here. But if you have if you play with the carrier concentration in your barrier, now this thickness of the barrier is very thick and it cannot pass through. And if your carrier concentration in the barrier is very, very low, then you see, now you can stop the tunneling barrier. And by changing different carrier concentration in your barrier layer, you can play with the barrier engineering, and you can confirm your ideas that if your material is really an intermediate band material or not. And this is the idea. Again, we made this by molecular beam epitaxy. We have a substrate, gallium arsenide. Okay, then we have N-type buffer, and we have an N-type L-gas layer, and this is a barrier, by the way. And this is an intermediate band gap material. Okay, then we have p-type barrier layer and p-type window layer. And because I want to make sure that how the barrier layer play, so I have doped 3 different doping profile, no doping, and 2 different profile. And just I wanted to show you that, okay, my intermediate band concept can play here. So let's say if you have a very highly doped material in your barrier layer, okay, my open circuit voltage, okay, is very, very less, okay, because I am missing my voltage. I told you, if you, okay, there is a lot of tunneling leakage. But if your carrier concentration in the intermediate band is, okay, a little bit lower, 4 times 10 to the power 16, you can improve the open circuit voltage. And if you have a very thick barrier, electron cannot pass through, so you see you have a very high voltage, okay? So this is what I'm trying to tell you, that we have to stop the tunneling leakage of an intermediate band, okay? And this is my, okay, summary that, okay, that how we can stop the long wavelength photon leaking through the tunneling. And this is, okay. So with that, let me summarize. So far I've talked, okay. At the first, I talked that we are working on different kind of material system, and we want to demonstrate twist of photon absorption, because that's the key idea for intermediate band solar cell. And we have done some density functional calculation, okay, and we did some film synthesis and characterization. And at the end, I tried to give you some idea that with this new kind of concept, okay, that one of the key idea is twist of photon absorption, but you have to design your barrier, okay, by doping or thickness and other things. So with that, let me stop, finish. But before that, let me acknowledge the group working here. So I have, in this work, 4 groups are working with me. The first group is Professor Yoshitaka Okada in our case, University of Tokyo. He's a quantum dot expert. Okay, another group is Professor Vladek Valukiewicz. He works in Lawrence Berkeley lab in the United States, also at the UC Berkeley. And third group, Professor Kin Manu. He has been in Berkeley a few years back, but now he is a professor in City University of Hong Kong. And I have a 4th group of this university in India, and they are collaborating with the CGS solar cells. And I'm going to appreciate this kind of funding agencies.